Hello and welcome to the 101 Earth Observation virtual lecture series. This series is delivered by the Satellite Applications Catapult in partnership with WILDLABS. This lecture is about a first overview of application, so what remote sensing can actually do. Let's start having a look of some potential application or some examples of use of remote sensing images. What we see here, it's an image in high resolution, optical image, from a sensor called WorldView 2 at about 50 centimeter of spatial resolution that shows the evolution of a refugee camp in Jordan, the Al-Zatari refugee camp. This is actually a series of images. So we see in 2011 how the land was, 2012, 13, till to the last one here. So what we are seeing here is how the refugee camp evolved through time. So we can see visible area of expansion. So this is particularly important, clearly, for planning. So to understand, for example, preparation to accommodate the number of refugees. So this is done simply by inspecting that area in high resolution with optical data. Another use of high resolution data, optical data, is to evaluate impacts of natural hazards, such as a tsunami. So in this case, we can see a region in Thailand, which is heavily affected by a tsunami in 2004. So we can see the image before the tsunami and after. So clearly, we can appreciate the destruction, in this case, caused by the tsunami itself. Another use of high-resolution data is to look, for example, and to plan, for example, to map crowds. This example here, it's over Munich at Oktoberfest. And we see, just zooming in the image, how it's actually possible to see individual persons there. This is particularly relevant in events like this one, where lots of people attend to direct crowds. But I think what is nice here is to appreciate really the detail and the spatial resolution of the image. By combining different sorts of images, it's actually possible to create digital elevation models. So we see an example here of a digital elevation model over London. We need a specific sensor configuration to generate this sort of imagery. But this is again something that is quite common, no? So that we see when we look at our phone, at applications that they use this information. So this sort of information is derived with remote sensing. Another type of application, which is a very remote sensing application, is the land cover classification. I showcased in a previous video how each part of the land behaves differently in terms of spectral characteristic depending on the land itself. By using this information, we can create a description of the land depending on the land cover, such as in this case over Munich, the Munich area in Germany. If we just take one of the land cover, for example, urban, we can see evolution of cities. So in this case, we see Istanbul in Turkey in different years, and we can study how the city evolved through time. So 75, 90, 2000, and 2010. So we see how basically the city expanded through the Bosphorus area. Meteorological data, it's an important aspect of remote sensing. So in this case, we see the snow cover in Europe through time. This has been generated by the German Aerospace Center, which you have also seen in previous slides. It's also called DLR. So in this slide, we see areas that are permanently slow cover, or we can appreciate the mean snow cover per year. So we can do studies, that study the snow, no, in the presence of snow. We can focus on specific components of the atmosphere as well, such as NO2, pollution. What we see here, it's an image, it's a difference actually, between two different times to see the change in NO2. So what is blue in this image as a decrease in NO2, and what is red as an increase in NO2 in two different times, in this case 2013 and 2007, so quite some time ago. Anyhow, you can see areas that are subject to a decrease in pollution, like in this case we see the United Kingdom and some areas in Europe, or some areas that they actually had an increase in pollution, such as some areas in Asia, where there is actually also some decrease probably around the Hong Kong area down there. Anyhow, this is good to appreciate pollution and to monitor it. We can see actually these and the impact that COVID had on NO2 again. So we see an example here over the United Kingdom, where we see that during COVID time, the lockdown period in 2020, we had like those level of NO2 level, while for pre-COVID period, so on the right, we have a much higher level of pollution. So you can easily appreciate this by looking at the color scale. Green, in this case, it's a low quantity of NO2, while red or violet is a high level. So this is clearly, we can clearly appreciate this by looking at these images. Hello, and welcome to the 101 Earth Observation virtual lecture series. This series is delivered by the Satellite Applications Catapult in partnership with WILDLABS. This lecture is all about passive remote sensing application. We have seen in the previous video an overview of application. Now we will look a bit more in detail some theoretical aspects that are within those applications. The first concept I want to introduce you, it's an important product from optical remote sensing, which is called Normalized Different Vegetation Index, or NDVI. This is an index, or it's a product, which is defined as in the equation over there. So it's a product that takes the near infrared and the red band and combine these properly to derive that product, the NDVI. Why this is important? NDVI is very important because it's used often to detect vegetation and to estimate generally a green biomass. It's very much related to vegetation health, as I will explain in the next slide. And there are clearly strong variation depending on the different season and even different year. We can see an example in this figure of a summer versus a winter capture of the NDVI. You can see actually how vegetation areas, they're quite captured here in green, just looking at this specific product. Why this relates to the vegetation health? So again, we are using near infrared and red bands, and we can see how a healthy plant in this case absorb a high quantity of red and reflect a larger quantity of near infrared, while an unhealthy plant or a plant that is just aging, as we have in the right, absorb a smaller portion of visible infrared and reflect also a smaller portion of near infrared. This absorption and reflection is linked to some physical phenomena and some specific physical aspects of the interaction of leaves and general vegetation with the light. and specifically to the quantity of chlorophyll that we have into plants. Anyhow, just putting the numbers here and just seeing those specific numbers into this NDVI equation, we see how the healthy plant in this case is an NDVI of 0.72, while the unhealthy, let's say, plant has a much lower NDVI, 0.14. This is the overall concept over this specific index. We see another example in the figure at the right, where the NDVI product is the colored figure at the bottom, and we see how the vegetation actually is captured very well, again, as a green, in green. In NDVI is not the only index. Optical remote sensing use several indices to capture different phenomena. An example of another index is an index that is proportional to the quantity of chlorophyll. So we see this index at the bottom of this slide. Why this is important? An example is, for example, to measure water quality. We have a specific example here of a lake in the Netherlands that it's quite important because it's a drinkable water reserve. So it must be kept free from algae. Algae means higher quantity of chlorophyll. And by studying, the quantity of chlorophyll into the lake, in the lake itself, we can actually, understand whether there is a good drinkable quality or a poor drinkable quality. So we see this in this plot. What is probably remarkable here is the spectral profile that we see. So this linked to a concept that I described before, which is the spectral resolution. You see this is a continuous line, but this is simply the link of different bands. So in reality, in this plot, we've got like 1, 2, 3, 4, 5, 6, 7, 8, and 9 different points which are linked together. So this is the spectral information that we have. And we can see how the lake has the spectral information that is like in red in the bottom. If you recall, in the second lecture, we have seen how water behaves like that. While an urban area, an agricultural area over there has a different trend. Now, this specific index look at the blue and the red part of it, and does like operation to understand whether there is chlorophyll and the quantity of chlorophyll or much or less quantity, as in the plot over there. Anyhow, the concept that I want to give you here alongside the application is the spectral profile. By looking again at the spectrum, we can understand other type of phenomena, more on the agricultural domain in this case, such as the health of potato crops. In this case, we are looking at nitrogen, and what is interesting here is to relate the quantity of nitrogen with our information, and we see this specific plot over here. Now, this implies clearly some modeling of nitrogen versus, in this case, we are looking at a specific part of the spectrum, which is called red edge, towards the red edge. So we have a red edge versus nitrogen here. So it needs this modeling. For this modeling, very often, and I'm linking to the first lecture, we need data on ground to calibrate this, or to understand which quantity of nitrogen corresponds to the specific red edge component. It's called red edge, by the way, because we are in the portion of the spectrum where vegetation has a steep increase over the red. So if you recall, again, in one of the figures that I've shown at the beginning, the spectral trend of vegetation is typically quite low in the visible part of the spectrum, then increase steeply over the red. And this is also called red edge. By studying that specific portion of the spectrum, we can study so many different properties of vegetation, such as in this case, the nitrogen. Another application with optical remote sensing is studying wildfires. So, for example, having a description of the severity of the wildfire. Again, this can be done through several indices, such as the burn index ratio, it is over there, or the difference of it. So there are several indices here. And we see also an example here of a wildfire shown in different bands. This has been captured with a specific hyperspectral sensor, which is called Hyperion. There aren't many hyperspectral sensors at the moment up there that provide with data. And if you just look at public hyperspectral sensor, there are very little. So Hyperion has been a mission that is actually has been there for many years, since like the early 2000s, and since for many years that was the only hyperspectral mission. Now there are several more, and one is mentioned there. It's called Prisma. It's from the Italian Space Agency, and it's also a promising one. Another application on pollution, it's more on mining and acid mine drainage. So this is when we have a mining setting clearly, and chemical reaction that are used within the mining, let's say, processing, are dissolved and transmit into the environment. This is a bad, actually, obviously a bad phenomena for the environment, and it's bad for many reasons, as you see there. So there is a potential contamination of drinking water, there is a corrosion of bridges, and there are general damages to the ecosystem. So clearly this is something that must be avoided. It's a major environmental contamination. Just as a statistic, there in the US, there are 10,000 kilometers of rivers that contains above safe concentration of metals, due to these operations. And it's still a major issue in some countries due to, for example, illegal gold mining and the release of mercury into the rivers. So those are all huge environmental issues. How can remote sensing help here? We can help in mapping it. So we can help him map, for example, the different minerals associated with that phenomena. Again, we are looking at the spectrum, so we see the spectral, in this case, characteristic of different minerals, and just by mapping this into the environment, we can have a description of the pollution. If we move to the sea side, we can study oil spills, and we can also inspect oil spills. Oil spills can be studied both with optical and radar data. In this case, we see an example of optical data, where again we are looking at the spectral description of the oil spill, and this was an experiment that has been done by the USGS. That was a lab test that was looking at the different component of the spectrum for different thickness of the oil. So they were looking, for instance, at the thickness of 0.5 millimeter versus something more, which I can read, but is in the figure over there. So basically, by studying the different, thickness of the oil and the spectral components associated to it, it's possible to classify it and to detect it. Another application, quite popular, is in the earth science. So, for example, looking at volcanic SO2 plume. So this is again looking at the atmospheric side in this case, and the atmospheric part of the of our planet, and looking at the signature of SO2, which is quite a unique one. This can be studied. In this case here, we see a couple of examples over the Hawaii Islands down there. And this is particularly important to study phenomena and to forecast also, the direction of the plume and the intensity of it. Moving a bit more into conservation, we have applications such as estimating colony sizes of penguins from space. This is quite a funny one, maybe, because an estimation of penguins in this case has been done in 2014 by looking at penguins' excrement, which appear, over eyes as like some color like pink or gray, as we see over there. So by studying specifically, those color and classifying very high resolution imagery, it was possible to detect colony sizes of penguins from space. Another application, it's on the seaside, is actually counting whales. In this case, high resolution data from, again, WorldView 2 has been used to detect the whales, in this case in Argentina. Now, for this specific study, the blue band has been used because blue slightly penetrate into the water column, and therefore if a whale is like, at the near surface but still within water, it's possible to detect it. And we see different signature here of whales. Final application, again with high resolution data, it's on counting elephants. In this case, we are in the savannah in Africa, and WorldView data has been used to detect elephants. An important point here, and also in the previous slide, is the use of what you read here, convolutional neural network. Is the use of artificial intelligence and deep learning for remote sensing study. So this is a big trend in the remote sensing sector, and it's used more and more each day. So the processing bit that I described in the first slide very often involves artificial intelligence, such as in this example. Hello, and welcome to the 101 Earth Observation Virtual Lecture Series. This series is delivered by the Satellite Applications Catapult in partnership with WILDLABS. This lecture is about active remote sensing application, specifically with synthetic aperture radar. Let's have before like a description of the application, a bit of overview of why do we need to use SAR. So we have seen that with optical remote sensing, we can trigger really lots of different applications. So why do we want to use SAR? Well, for a few reasons. Very often SAR is used when optical data is not available due to cloud covering. And that's a big use of it, actually. You can think to regions where, I don't know, maybe in the Amazon region, where it rains very often for several parts of the year. And if you want to do a study over there, specifically over there, we can't really use optical data because we would always see clouds. So SAR is in this case used. Actually, the second point here is also important, that very often they can be used together. So to increase the accuracy of our products, for example, land cover. Other peculiarities on optical remote sensing are written there. So penetration into canopy. So optical data would simply see the top of the canopy, while several microwaves of synthetic aperture radar can actually enter into the canopy and see the soil. So this is an advantage of using SAR data. Another use is on deformation monitoring, such as slope stability studies. This is another advantage versus optical data. So I mentioned in the theoretical overview of SAR that there were two components of SAR images, amplitude and phase. Just looking at the phase in this case, we can study how the ground is moving with millimetric scale, as we will see later. Or we can go a bit more into physics just by looking at different properties of the signal, called polarization in this case, to study, for example, the physical composition of crops. As I explained, SAR remote sensing is actually more complex than optical remote sensing in terms of pre-processing. So there are several steps that might be needed to get this sort of products, and this sort of product it's also called very often analysis ready data, which is data that is ready to be used either to do a processing such as a land cover description, or used on its own to do classification or whatever. First application is on deformation. So you see in this figure here a colorful overview of London, where we have areas in red and areas in yellow and areas in blue. So what we are actually seeing here is the ground deformation. And while yellow it's basically a stable area, red and blue, there are areas that they move up and down, so the subside or the uplift of a few millimeters. So what we can appreciate maybe here, it's like this line that goes around the river, so this red line. So this is actually the construction of the Crossrail, so which is like an infrastructure. It's a transport mean in London, and the construction can be actually very much identified by subsidence pattern all around it. We can do this with SAR, and this is very relevant for civil engineering application, for planning or for studying construction works. Other example here, actually what we have is typically in form of single measurements, and the displacements over here are single measurements over a city in Turkey. This is coming from a study that I have personally done. So we can see measurements here of subsidence or uplifts in this specific city, which is called Rize. And let's appreciate here the values. So millimeter per year, and the values are 2 millimeter, 3 millimeter, 10 millimeters. So we are looking at something that is really small. This is particularly impressive when we think that synthetic aperture radar satellites, they're actually flying at about 500 to 900 kilometers, far away from the Earth. And they're able to capture this information with that so small values, so just millimetric values of deformation. This is quite impressive, and in this specific paper, you can see how actually you can detect cracks in the house just looking at those values, so differential settlement and so on. That's a video from the German Aerospace Center that showcase how a point cloud generation can be actually shown in 3D. So this is another mean of getting digital elevation model. So all those points that are actually properly geolocated. I have shown before how optical data in a previous video, how optical data can be used in agriculture. SAR data can be used as well in many different applications, as we see here. So from detecting the phenological stage to a mapping of crops, to studying specific components of crops, such as soil moisture, the condition, leaf array index, or even getting the height of plants, as in the video shown there. So SAR is also very much used in agriculture. Another use of SAR, which is quite common, is to map flooding and also to predict flooding. So in this case, we have a map which is actually a prediction of flooding. So with areas that are at very high risk to very low risk. So flood maps and flood mapping, it's very much a SAR application. The reason behind it it's how SAR behaves with water. So water, they're mainly a mirror to SAR, because we got our signal that is like bounce the water and then bounce back. The bouncing is not directed towards the sensor, but is a sort of like it's mirrored away. Therefore, we have a very little signal for water, and it's quite easy to detect water and therefore to detect flooding. Another use of SAR data is for deforestation and forest studies. So we can see an example here of deforestation patterns from a high-resolution sensor from a commercial company called ISI, and we have two different timing and different deforestation. We see how deforestation appears as darker in this case in the SAR image. But this sort of study can be triggered with SAR data. Earth science again and volcanology is also a SAR-friendly application. We studied, for example, on deformation and looking how the ground subside over the area, and related studies, or mapping of different phenomena, such as mapping lava fields, mapping cauldrons in case of glaciers, and so on. And finally, again, this is linked to what I mentioned before about water, ship detection. So this is another example from the German Aerospace Center, where we have like different ship which are detected with a sensor called TerraSAR X. In this case, it's another commercial sensor that delivers high resolution data. So we see how ships appear very bright in SAR images. So why? Because, as I explained before, waters appear as dark, and ship like stand out in a SAR image. Therefore, their detection can be a task that can be performed with SAR images.